Okay, thanks for the very kind introduction, Dick. Okay, so let's get started. So I guess most of you work in one way or the other on algorithms. So what you're usually trying to do is that you have your favorite problem that you're working on, and then you would love to come up with an algorithm where you can show it's an efficient polynomial time algorithm. But life is not always that nice and that easy, as you may have figured out. So not every problem actually has an efficient algorithm. This is one of the classical problems that probably is hard. And let me just remind you, this is the Hamiltonian circuit problem. The input is some undirected graph. And you only have to answer a question. Does this graph contain a cycle that visits every node precisely once? Something like this. So this is an NP-complete problem. For questions, I refer to Dick, what the definition of NP-completeness is. What this actually means is that Hamiltonian circuit belongs to a large class of at least thousands of known problems that are all kind of have the same hardness in the sense that you can reduce every of the problem to every other one. And it has been conjectured that there is no polynomial time algorithm for this big class of problems. This is the P versus NP problem. This has been around, well, at least since the 70s. It's on the list of 7 millennium problems, and there's an award of $1 million if you want to solve the problem. And that's probably the hardest way to earn $1 million these days. Okay. So if I show that there is no efficient algorithm, I always find this as a bit of a vague statement, but it's a very precise way of stating this. It's nice to phrase the problem as a circuit problem. So you can imagine you can phrase whatever NP-complete problem you have. You can define a Boolean function, which may look like this. Imagine this is a Boolean function representing your Hamiltonian circuit problem. The function has some inputs, let's say n many inputs. These are bits, and it has some output, which is also going to be some bit. And if you wonder how you put your Hamiltonian circuit problem in this, then you could say that let's say you order the edges in a complete graph. You denote them by E1 to En, and then the ith input bit is just whether the ith edge is in your input graph or not. So this way you can represent every graph on about root and many vertices. You can represent that with the 0-1 string of inputs, and then this function should tell you whether that represented graph does contain a Hamiltonian circuit or not. And so everything you have to do is that this Boolean function needs to have a large number of gates. And if you can see some made-up example of gates here. For example, this is an AND gate. It gets 2 bits as input, and it has maybe 1 bit as an output. There's an OR gate, and there are also NOT gates. And the question is, like, how many of these gates do you need to represent that function? And the P versus NP question, it's basically equivalent to showing that whatever NP-complete problem you have, the number of gates you need is super polynomial. Basically equivalent modulo some small technicality. Okay. So this is clear? Okay, so this is a nice and concrete question. Now we can wonder, actually, what do we know about like the number of gates you need for certain explicit NP-hard functions? So 30 years ago, the state of the art was a lower bound of 3n for some explicit function, actually a very simple function, something explicit. And now, thanks to 30 years of extensive research and millions of dollars of very well invested taxpayer money, we can improve the second digit behind the comma. You could be mean and interpolate that at this speed of progress, it takes around 3,000 years until we reach a 4n bound. Progress is somewhat slow on this side. Actually, as a little anecdote, there's a nice webpage of Gerhard Wöginger where he lists all the attempts of people trying to prove whether P equals NP or not. The last time I checked, he had 116 archive submissions of some people proving, well, submitting like some wrong claims, probably wrong claims about a solution. And I think this is pretty unique in like the whole area of mathematics. I'm not aware of any problem where people submit that number of incorrect submissions. Okay, I want to talk a little bit about one of the early claims, which is actually by a Canadian mathematician, Swart. That's from the middle of the 80s. He claimed that P would equal to NP. And the way that he claimed he had solved the problem was by modeling the Hamiltonian circuit problem that I just defined as a linear program. Nowadays, we would be very quick to just dismiss these kind of attempts. I digged out one of the old Optima newsletters. This is the one from '86. And if you read this, then you see that, well, if correct, it would be a revolutionary claim. It is only professional to be suspicious, but at this time, we know of no one who has either verified the approach or proved it fatally flawed. So in other words, that time, it was actually plausible that it could have been true. Let's phrase it that way. Okay. I want to explain a little bit more about this. So first of all, what is that linear programming that I talked about? So linear program, it's kind of a mathematical optimization problem of a simple form. You have some inequalities, some linear inequalities. Your solution is some continuous vector in R to the n. And what you're trying to do is you're trying to, let's say, maximize some linear function. This is best explained in a little picture. So if you draw the half spaces belonging to this linear system, you get some inequalities, and the intersection, like the set of solutions to this system, it's going to be of this form. It's what is called a polytope. And if you now try to optimize a linear function, then you can see that, well, if there are vertices, that you're going to be optimal at one of the vertices of the polytope. Okay. So linear programs can be solved efficiently, both in theory and in practice. In particular, the folks over in operations research, they love their linear programs, because whenever you can model your favorite problem as a linear program, then you're kind of done. You know that they are very good algorithms to solve your problem. Okay. And so it's not completely, back in the days, it was not completely insane to hope that linear programs, as they are quite powerful, that they could solve your NP-hard problem. Okay. There's one detail that actually linear programming, it's a continuous optimization problem, and Hamiltonian circuit, it's a discrete question. It's the set of solutions, it's discrete, it's a finite set of solutions. It's not a contradiction if you think about it. The way how you can model, in principle, model every optimization and every discrete optimization problem as a linear program is the following. You can look at the set of your solutions, let's say the characteristic vectors of your Hamiltonian circuits, let's say in a complete graph. They are in some high dimensional space. These are 0, 1 vectors living in some high dimensional space. And you can look at them, and you can look at the convex hull of them. And if you had some basic course on linear programming, then you know that the convex hull of a finite number of points, it's actually also a polytope. In particular, you can also represent the same space, the same set of solutions as just the intersection of a finite number of half spaces. So you can also write it in this inequality form. And now if you have a concrete graph and you want to know whether your concrete graph does contain a Hamiltonian circuit, you can do the following. You can take the characteristic vector of that graph. So it's a 0, 1 vector that has ones wherever you have an edge. And you can just optimize it over that space of solutions. And you'll get some optimum. And then you only need to see whether that optimum point, well, it will correspond to a Hamiltonian circuit. And then you just need to check whether that Hamiltonian circuit is actually in your graph. And if that's the case, then the answer to your question was yes, this graph does have a Hamiltonian circuit. Otherwise, it doesn't. Okay? So this is a fairly standard approach to model your problem, your discrete problem as a, let's say, linear program or as a polytope. Is there any questions so far? Okay. So this is somewhat what Swart had in mind. If you think about it, what is actually the important quantity here, then, well, you can solve the system efficiently with a linear programming solver, well, as long as the number of inequalities is small. So that's kind of the number that you care about. Okay. So naively, one might think that the only thing you have to do is you have to count how many facets does this object, this polytope, have. And that would give you the number of inequalities. But actually, linear programming is a little bit more powerful, and that's not exactly the number that you should look at. So I will explain why not. Okay. For example, let's look at this polytope, which, imagine it lives in 2 dimensions. It lives in the plane that's a little bit tilted. And if you count, then this object has 8 many facets. So you would naively need 8 many inequalities if you wanted to represent that polytope. Okay. But now let's look at this 3-dimensional polytope. And so this 3-dimensional polytope Q up here, it has 6 facets. So if you think about this geometrically, you could actually represent this with 6 many inequalities. Moreover, if you imagine you're projecting down this polytope, and if I did draw things correctly, you would actually project down, and the shadow would be P. So what this actually means is that there is some lower dimensional polytope with many, 8, many facets, but it is the projection of a higher dimensional, or higher, like 3, dimensional polytope that has fewer facets, that has fewer inequalities. From the mathematical programming perspective, what you're doing is that you have a problem that needs a lot of inequalities in the original space, but now you're adding some extra variables to your linear program, and that reduces the number of inequalities that you need, possibly dramatic. So there are actually examples where the original polytope has needs exponentially many inequalities in the original space, but after adding some extra variables, it needs only polynomially many inequalities. Okay? So there is some mechanism that actually allows linear programs to be quite powerful in many settings. And in particular, it's not very clear whether this power is enough for solving a Hamiltonian circuit. Okay. This is maybe a little bit abstract. I want to go back to Hamiltonian circuit and explain a little bit how maybe one could cook up some linear program. Okay. This is a linear program that tries to model Hamiltonian circuit. This is actually from the literature. This is the so-called Subtour elimination LP. Okay, so let me try to explain this. So there's some, okay, so what we're actually trying to do is that we're trying in some graph, we're trying to find a Hamiltonian circuit, and let's imagine we're directing the edges. So we're trying to find something like this. And there are some more edges around, okay, that I'm not drawing. Okay, so if you model this as a linear program, then you may want to have some variables xe that tell you whether you want to use that edge in your Hamiltonian circuit or not. Okay. Okay, so what is actually a Hamiltonian circuit? If you look at it, like for every node, you have one incoming edge and you have one outgoing edge, if you gave things directions. Okay, so maybe you want to add that as a constraint. So for every node, if you sum over the outgoing edges, that's 1, and if you sum over the incoming edges, that's 1. Okay, so far so good. Now you're wondering, is this enough? Well, not really. Maybe what you have is something like this, and this is a beautiful subgraph where outgoing degree is 1, incoming degree is 1, but it doesn't actually really look like a Hamiltonian cycle in the sense that this thing is not connected. So you need to act something that gives you connectivity. There's several ways how you can do that. This is the one that I'm choosing here. I say that, well, for every u and every v, there should be a way to go from u to v using the edges that you just bought. And that's not satisfied here. But you could satisfy it with the following constraints. These are some extra variables. So it means that actually this is already, we already use extra variables here that we actually would need. Now this says that, well, if you stare at every pair uv, there is, well, it's a flow of strength 1 going from u to v. So this actually ensures that there's a way to go from u to v. So this gives you some kind of connectivity. Okay. Okay. So question would be, now if you solve this linear program, which you can do efficiently, is this going to give you an answer to your Hamiltonian circuit problem? No, it does not. Because this is an example. This is a graph that people working in the field have seen like a billion times. You can put, if you put xe weights like this, a quarter on the thin edges and a half on the thick edges, then this thing will satisfy these constraints. You also have connectivity, but there is no Hamiltonian circuit contained in these edges. So it's kind of the linear program would tell you a false solution. The linear program is feasible even though there is no Hamiltonian circuit. Okay, so is this the LP that Swart claimed was doing the job? No. Basically what Swart was doing is that he had a more complicated linear program with more variables, more inequalities. But basically it had the same issue, that there was some fractional solution that actually would not correspond to a Hamiltonian circuit. If you want like a geometric picture of the whole story, then you can imagine that this is the solution space somewhere in some high-dimensional space of the subtour elimination LP, and this might be the actual convex hull of the Hamiltonian circuits, with like every vertex corresponding to a 0, 1 vector of a Hamiltonian circuit. And the problem is like this solution here that I showed you in that space, it would be like one of these points here. So there would be points that are feasible for the LP, but they are actually not in the convex hull of the Hamiltonian circuits. Okay. Okay, so far so good. But the issue is, did Swart actually have any chance of being correct? So in the sense, if now someone publishes a paper saying that, oh, I can solve Hamiltonian circuit with a linear program of polynomial size, might that person actually be true? Do you need to spend hours and hours finding a bug in the paper? To be precise, do you need to have your graduate students spending hours and hours of the weekend finding the bug? So I want to actually give you the answer to this question, okay? And in particular, I think the graduate students are now listening. Right? Okay, actually, good. Okay, so there was a partial answer actually very quickly after Schwarz's result. This is it's a beautiful paper of Yannakakis. And I believe Yannakakis actually looked at Schwarz's paper, and what he observed was that the suggested linear program, it was symmetric in a certain sense. And if you can imagine that if you have a graph and you're looking for a Hamiltonian circuit, you probably won't write down a linear program that kind of treats vertices, differently. It's kind of probably if you rename the name, if you rename the vertices, you could also rename the variables in a certain way that actually your linear program hasn't changed. And Yannakakis could actually prove that any such linear program that satisfies the symmetry assumption, any such linear program for the Hamiltonian circuit problem must have exponential size. And now it sounds like we're almost done, but there's actually no mathematical reason why, for whatever problem, a symmetric linear program should be the best. In fact, there are some examples where one can prove that this is not the case. So it's a partial answer. It's a strong indication that, one should be able to remove this word of symmetric, this assumption. But it took a surprising quarter of a century until some people, including some of the participants of the current program, proved that there's actually no linear program whatsoever for Hamiltonian circuit. So in particular, this is the paper by Fiorini, Massar, Pokuta, Divari, and de Wolf. And the lower bound they have, it's exponential or sub-exponential, however you want to call that number. So that's great. It means you can just read the abstract of the paper and then reject it. So it's a wonderful way to preserve capacities if you're a reviewer. Okay, and I want to talk a little bit about this. Result, just how in principle could you prove such a lower bound? Because this is a completely unconditional lower bound. And you should compare this with the, pretty much failure of lower bounds for general circuits. And if things are getting too technical, please stop me, slow me down. I think we have a little bit of time.
So why is this really the focus, the size or the number of constraints in the linear program where you can have a separation algorithm solved in polynomial time with ellipsoid method?
Correct. So this result does not rule out that you have a separation, that you have a polynomial time separation oracle. And I'm pretty sure that if you rule out a polynomial time separation oracle, then you also have proof that P is not NP. Yeah. So in some sense, this is like the only thing that you can do before you end up on Gerhard Wöginger's webpage. One way or the other. Maybe you end up, like the only good paper. But anyway, okay, so let me explain a little bit. Okay, so to be precise, the lower bound does not directly apply to that convex hull of a Hamiltonian circuit. It applies to a different polytope that's called the correlation polytope. But you can transfer the lower bound by observing that the correlation polytope, it's actually, it linearly maps to what's called the phase of the Hamiltonian circuit polytope. And then if there is no small linear program for this thing, there is no small linear program for this thing, because otherwise you can just set some of the constraints as inequalities, and you also have a small linear program for this thing here. So, okay, this was an unconvincing.
What is the correlation polytope?
And we'll come to that. Yeah. We'll come to that on one of the next slides. So, okay, but just don't be confused if I show you a lower bound for something that's not the Hamiltonian circuit problem polytope. But there's a pretty simple reduction. It's like kind of like one of the simple NP hardness reductions here. Anyway, okay, good. So one of the very basic concepts in this whole theory of like how small my linear program has to be, it's the concept of a slack matrix. So let me try to explain you that. So let's take a polytope P, and let's look what the slack matrix should be. It's a huge matrix, which for every of the facets of your polytope, like this is a facet of your polytope. For every facet, you have a row, and for every vertex, you have a column. And the entry that you have, it gives the slack that the vertex has with respect to that facet. Okay? So it's some non-negative number that basically is proportional to the distance of the vertex to that hyperplane here. Okay, so it's a giant matrix. For most polytopes, you have exponentially many rows and exponentially many columns. Okay. So the next concept that you'll need is what's called the non-negative rank. So like probably everybody of you knows what's the rank of a matrix. The rank of the matrix asks to factor a matrix as U times V, and these are like smaller matrices where you're trying to minimize the number of columns of the left factor and the number of rows of the right factor. That's the rank. And the number of columns here that you need, that's the rank. The minimum number is your rank. Okay. And non-negative rank, it's an extension where you require that both of your factors, U and V, both of the matrices that you're using to factor S, they only have non-negative entries. And that's the non-negative rank. So in particular, the non-negative rank is a quantity that's always at least as large as the usual rank, but it may be a lot higher. Okay. And good. So why am I explaining this concept of slack matrix, non-negative rank? Well, actually, I want to talk about the size of linear programs. And here is the very useful theorem of Yannakakis back from the end of the 80s, which is the following: that you can take any polytope, you can look at the slack matrix S, and the smallest number of inequalities that you need for something higher dimensional that projects down on P, so this is called the extension complexity. So this quantity that we actually want to lower bound, it equals the non-negative rank of the slack matrix. Okay? And this yes?
For arbitrary LPs now or still symmetric?
This is for arbitrary. Yes, yeah, it's a good question, thanks. Okay, so this is good because we're trying to bound something geometric, like the number of inequalities that some object needs that projects down on your target polytope. And we can do something that looks more concrete. We can just look at that slack matrix of your polytope, and we can just bound the non-negative rank. It's not that we would know yet how to do that, but it sounds like this is something, it's something nicely algebraic. Maybe one can do something. Okay. And in fact, that's the way how it goes. I don't want to go too much into the proof here. The first time you see the claim, it's not so clear why this should be true. If you stare at a picture, you might get an idea why. Okay. So give me 1 minute. Okay, so this is our target polytope P, and if you look at one of the facets and one of the vertices, then this vertex has some distance, some slack with respect to this constraint. And now, if you look at something higher dimensional that projects down on P, then actually this constraint, it must be a non-negative combination, a non-negative linear combination of normal vectors up here. And if you look at this vertex and you look up here, there's going to be some point in Q that projected down here. And this guy here, he also has some distances with respect to those constraints up here. And now if you take the same non-negative combination of the distances that this guy has with respect to inequalities here, then you're actually getting precisely this distance to this guy, to that inequality here. It's a little vague, but it's like a one-line calculation. If you write things down and you stare at it long enough, then you actually see that this is going to be true. Okay. Okay, so let's take this as given. Okay, good. Okay, so there's going to be one principal problem that, okay, if we want to show lower bounds for the size of linear programs, we have to show a lower bound for the non-negative rank of some huge matrix. But how do we do that? And there is a very nice combinatorial way of lower bounding that non-negative rank. And that's by looking at what's called the rectangle covering number. And I'm trying to explain you how that works. Okay. So let's look at a non-negative matrix S. And let's look at some non-negative factorization. So in particular, if you look at this matrix, then this matrix, you can factor it as U times V. And these are also non-negative matrices. Okay? Now we're kind of lower bound like the number of columns and the number of rows here. And it actually suffices to only look at the support of the matrices. So you forget all the numbers. You just look at, are the numbers 0 or are they strictly positive? And if you now look at the first column of U and the first row of V, then there are going to be some positive entries. And the product of a positive entry and a positive entry plus some other non-negative numbers is going to be something strictly positive. So wherever you have something positive here, you will have something positive here. So in particular, if you look at this, the support of this column and the support of this row, then their Cartesian product is going to be what's called a combinatorial rectangle in the support of S. Okay? You can play the same game with all the other rows. And in particular, you can see that every of the positive entries in S is going to be covered at least once. But none of the 0 entries is going to be covered. Okay. So that gives us a beautiful lower bound in the sense that the non-negative rank of this matrix is going to be at least the number of these combinatorial rectangles that you need to cover the support, where none of your rectangles is allowed to contain one of the 0 entries. It's a nice combinatorial lower bound that may be good or may be bad. You don't know. Okay? The nice thing is this is going to work for our case of that correlation polytope that I still haven't yet defined. Any question?
So, I mean, you can take combinations of any vector in U with any vector of V. So I would expect to get something like R squared combinatorial rectangles in S, not just R.
So you're thinking about like this product with these guys. Well, there's no product. It's like if you like this number here, it's this product plus this product.
Oh,
but
yeah, okay.
Okay. Good. Finally, ladies and gentlemen, the correlation polytope. It's defined mathematically in a very compact way. You just take every 0, 1 vector, and then you take the outer product with itself. And you take the convex hull. So for example, for n equals 2, you just look at the convex hull of, think of these as being like n square dimensional vectors. So these are like n square dimensional 0, 1 vectors, well, actually n by n matrices. So these are all the n by n matrices of rank 1 or 0. Okay. By the way, it's an NP-hard polytope in the sense that it kind of allows you to optimize quadratic functions. So it's not too hard to show that optimizing a linear function is NP-hard over this polytope. Okay, but we will show that the extension complexity of this thing is exponential. Okay, so now what you should do is first of all, you should know what is the slack matrix. So that's a little bit of an issue. Okay, so the vertices of the correlation polytope, they are of a very easy form, like very explicit form. That's nice. We actually don't know all the inequalities describing the polytope. There are reasons why we will never know all the inequalities explicitly, but there is a nice family of inequalities that we can explicitly write down, and it goes as follows. You take any 0, 1 vector A, and you do the following. You take twice the diagonal matrix you get out of A minus AA transpose, and that multiply with any point in the correlation polytope is going to be at most 1. Okay, you can take my word for it. You can sit down for a couple of minutes and do the math, do the calculation, and it actually suffices to see that what is the distance, what is the slack that every vertex has with respect to P, and then by convexity reasons, you will also know that every point inside of the correlation polytope will have a non-negative slack with that inequality. Something very beautiful happens that if you look at a vertex of the form BB transpose, then its slack with respect to this inequality, it's precisely 1 minus the number of ones that A and B have in common squared. So it's a very nice explicit formula that you can get. It's also nice that something squared is always non-negative, so that's, this seems right. And in particular, the claim that one can prove is that the corresponding slack matrix of this thing, it will have a high non-negative rank. Okay, so this is the slack matrix that I mentioned. We can get a row for every 0, 1 vector A. We can get a column for every 0, 1 vector B. And then the entry that we're going to see here, it's the formula that we just figured out. It's 1 minus A intersected B square. Okay. So what remains to be proven is that this thing has a high non-negative rank. Okay. And this is just a one slide outline, and then the hardest part is done. Okay. In particular, there are two types of entries that are particularly interesting. If you look at this, if A and B are disjoint, if these are 0, 1 vectors and they don't have a common 1, then this is 0, so you have 1 minus 0 squared, so you'll see a 1 in the matrix. And if A and B share precisely a single entry that is 1, then you will see a 0 here. And zeros are particularly important for this rectangle covering lower bound. Okay, so what remains to be proven is that if you're trying to cover the 1 entries, the positive entries here, with combinatorial rectangles that are not allowed to include 0 entries, then you need exponentially many of them. Okay. Okay, so you can do a little bit of counting, like how many of these entries do you see? Okay, so how many 0, 1 vectors in n dimensions can you get where they're disjoint? You never have a 1 at the same position. They are precisely 3 to the n. Because for every position I, there are 3 choices, like both 0, 1, 1 here, or 1 at the other vector. Okay. And so the only non-trivial thing that you need to prove, and that I will have to skip here, is that you need to show that whenever you have a combinatorial rectangle, then it's never going to contain more than 2 to the n, more of those 1 entries here. Assuming that the rectangle doesn't contain any of the 0 entries here. Okay. It's a 1-page combinatorial proof, very elegant, but I'll have to skip it here.
Is it tight? The 2 to the n?
2 to the n, probably. For correlation, yes. Okay, sorry. Okay. This lower bound, probably not tight. There's a 2 to the n upper bound, I think, that's not hard to get. 3 to the n, I don't think that this is tight. Okay, so where is this lower bound coming from? Well, you have 3 to the n many, number like entries you have to cover. Every rectangle covers only that many. So the ratio of that's the lower bound on how many rectangles you need, and that is a lower bound on how many inequalities any higher dimensional object needs that projects down on the correlation polytope. And that is actually the end of this story. Okay. Well, that's the end of the proof. It's not the end of the story. Any questions? Yes.
Yeah, to follow up on this separation thing, it's not impossible to show that you need exponential number of constraints and there is no separation. It's not going to create any breakthrough result, because it will only tell you that if you are to prove that NP is equal to P, it's not going to be via linear programming.
I don't know. I would disagree.
So suppose you could show that it requires exponential number of constraints and without separation, without the polynomial separation algorithm.
Okay, so for example, let's look at that correlation polytope. So if you rule out that there is no polynomial time, you show that there is no polynomial time separation. That also shows that there is no polynomial time optimization problem, because you have an equivalence between polynomial time optimization and polynomial time separation. So you're showing that I cannot in polynomial time optimize over the correlation polytope. And that's an NP complete problem. So I think it would actually show that P is not NP.
Yeah, I don't understand that.
Okay, so good. So this is a little bit, yeah, that was kind of the state of the art after the paper by Fiorini et al. Actually, let's do a little bit of thinking here. So there is an NP complete problem where we have proven that there's no polynomial size linear program representing the corresponding polytope. On the other hand, actually linear programming, it belongs to some of the hardest problems in P. There's a way how you can make this formal. You can show that you can take any problem in P, and there's a reduction that only needs log space, and you can transform that into a linear program, and then the solution to the linear program is going to tell you the answer to your problem in P. So can you put both things together? At least for some time that people were actually wondering, like, could this going to be a path to proving that P is not NP? Unfortunately not. So this is not going to work, and try to explain you why not. In particular, there's going to be an easy problem, like computationally easy problem, where we can also show that there is no small LP for it. And this is going to be the matching problem. Okay, so first of all, what is a perfect matching? A perfect matching in a graph, it's a pairing between vertices where every vertex gets paired precisely once. And now you can again look at the corresponding polytope, which is going to live in some high dimensional space, dimension corresponding to the number of edges in the graph, and every of the vertices, it's going to correspond to the characteristic vector of one of the matchings, one of the perfect matchings. So it's going to be like, again, some 0, 1 vector, same story as for Hamiltonian circuit. Differently here, for this polytope, it's a computationally easy polytope in the sense that if you give me any objective function, you can actually optimize in that direction in polynomial time and find the optimum vertex. And this corresponds to putting weights on the edges of your complete graph and finding the maximum weight perfect matching in that graph. There's a polynomial time algorithm already known since the 60s due to Edmonds. On the other hand, one can actually prove that if you try to represent this polytope as the projection of some higher dimensional object, that object will still require exponentially many inequalities. So there is no way to solve the perfect matching problem by a single linear program. Strangely, you can solve it with, with a polynomial number of different linear programs, but not with one. So this means that if you go back, I don't think you'll have a chance to use much of the technology that has been developed in proving lower bounds for linear programs to also show lower bounds for circuits. So that may not work. Okay. So there are some extensions more recently for semi-definite programs, and if I have 2 minutes, I'll give a brief overview. A semi-definite program, it's of the form that you have a matrix that you require to be positive semi-definite and symmetric, and there are some linear inequalities. It's not always easy to imagine how this object looks like. If you write down some example, then you see that actually it's a convex program. So the set of solutions capital X is going to be convex. It's in general not polyhedral. So that convex set, it can have an infinite number of you may need an infinite number of inequalities, so to speak. They're kind of the form that, well, I mean, this is equivalent to saying that this thing is positive semi-definite. It's like saying that x times some the outer product of a vector with itself should be non-negative. So you have an infinite number of constraints of a very particular type. And semi-definite programs, they are more powerful than linear programs in the sense that there are some beautiful results that you can use an SDP to get a good approximation for max cut within 13% of the optimum, but you can't get better than 2 with this polynomial-sized linear program. So by now, we actually have a very clear separation between what a semi-definite program can do versus what a linear program can do. And a little bit the end of the story is that by now, there are also lower bounds for the size of semi-definite programs, also for that same correlation polytope. And they're also somewhat of exponential size. Then the last one is by Lee, Raghavendra, and Steurer from 2 years back. Okay, I'm a little bit at the end of my talk. Open questions. There is the obvious one is that there was the problem that we actually want to solve is show unconditional lower bounds for algorithms or equivalently for circuits. We still don't know how to do that. But if we can do that, if we can't do that, can you maybe at least show lower bounds on classes of algorithms that are meaningful? It's not so clear what classes that should be. Maybe some general type of dynamic programming, something algebraic. Can you show me lower bounds on classes of algorithms that cover a good chunk of polynomial solvable problems, preferably including matchings? And that would be a nice thing. But I'll close here and thank you.
Take some questions.
So the lower bound from Fiorini is sub-exponential. Is this improved now, or is it still the best that we know is sub-exponential?
I think a 2 to the n bound, you get it from the matching result that I had. So you get some slightly improved bound from my matching bound, yes. And I think and probably that's the best possible, yeah.
With regard
Go ahead.
with the bounds, you have this rectangle cover as a lower bound. With a nice, simple way to get a lower bound.
Yeah.
Is there any cute upper bound for extension complexity that's similar? Like some geometric property that says have a formulation of an exercise?
Nothing out of the top of my head.
Other questions?
It's more of a comment that matching actually can be solved with one linear program with ellipsoid method, with separation. And in fact, if I'm not mistaken, Padberg and Rao, I think it was in the 80s, showed for the first time that the B-matching problem is solved in polynomial time via ellipsoid with separation.
Okay.
So the issue of separation, I think, is really kind of fundamental in all of this.
Well, the point is, like, for separation, you're allowing an arbitrary polynomial time algorithm, and yeah, these approaches don't rule out that. Yeah.
If you allow a huge number of extra variables, then you can control the size of the coefficients in the facets. So, right, I mean, you just write a convex hull representation. So, what about sort of in between? If you look at, are there cases where bounding the size of the coefficients forces you to have the extension complexity jump dramatically?
Well, this is not captured in the lower bounds. The lower bounds say I don't care about that, and I don't have a nice example where you would have a separation, where there is a small LP with ugly numbers, but there is none with like polynomially bounded numbers. I don't have that.
Any further questions? Let's thank Thomas again.
Okay.